Hello guys, welcome to session number 12 of our KCET 2023 one-shot series. Today's topic would be thermal properties of matter, as you can see, and the bracket is written as 0.99, which means approximately one question has come every year from this chapter. So yeah, it's pretty important considering the overall class 12 marks as 15. So yeah, the first topic, as you can see, will be conversion, which means that let's say, as you can see, the formula over here would be r minus I by s minus I is equal to constant. So if you're wondering what this formula basically means, because I can agree that it doesn't really say much for a person who doesn't know the meaning of the notations. So yeah, I'll be just explaining it. R means it's the reading, and I means ice point, and S means steam point. So that basically means at 100 degrees Celsius, 0 degrees Celsius, and so on. Ice point and steam point is what we call for I and S, and R is reading. I hope you listen to me carefully. I'll be presenting you with an example. So as you can see, I've written the steam point and the ice point for all of them over here. So this would be the steam point and this would be the ice point. So I'll just be going down a bit. Yeah. So the steam point for degree Celsius would be 100 degrees Celsius, and for Fahrenheit it would be 212 degree Fahrenheit for steam point, and for Kelvin, as you know, it would be 373.15. So ice point is 0 degree Celsius, 32 degree Fahrenheit, and 273.15 Kelvin, as you can see, would be the ice point. So the use of this is, let's say I ask you a question saying what is 80 degrees Celsius in Fahrenheit, or let's say in Kelvin, I ask you in Kelvin. So obviously there are going to be a formula you have learned in maybe lower grades, but this formula will from now onwards help you. So all you have to do is you have to write 80 because that's the reading, which is either given or asked. That's why it's equal to constant, which means you have to basically equate it to the same thing, but I'll show you how. So as you can see, it's 80 degrees Celsius. So 80 minus 0, because it's 0 degree in case of Celsius, it's 0 degree Celsius as ice point, and S again, steam, meaning 100 minus 0 is equal to, and one more thing is I'm using a mouse, so yeah, please do pardon me for the bad handwriting while writing here on annotations. So yeah, I'm not using the writing part. Is equal to, as you can see, R should be used now, because in this case we don't know the reading. This is something to be found, this is given, so that's the difference. Once when you're equating this side, it should be given, or here it should be the one which is asked, minus, as you can see, ice point over here would be 273.515. Obviously you can avoid the decimal in case of MCQs, because you can easily figure out the nearest value. And as you can see over here, S minus I over here would still be 100, because S would be 373 not 100 actually, 373.15 would be steam point, minus ice point, which is basically 273.15. So while you solve this, you'll be able to find the value of R. As you can see over here, this R can be found out, and yeah, that's the application of the formula. I even told you the application, meaning of the notation, and all of it. It comes in handy in all kind of chapters where the conversion is needed. Students can use this formula. So yeah, next one would be expansion. As you know, there will be three types of expansions. There will be linear, superficial or aerial, and volumetric volume expansion. So for linear expansion, it is basically over here, as you can see, the formula delta L is equal to L alpha delta t. Over here, delta L would be the change in length, L would be the original length, alpha would be coefficient of linear expansion. Please listen to me carefully. Alpha is coefficient of linear expansion, and delta t would be the change in temperature. So LF, meaning the final length, would be equal to delta L plus the original length. That obviously makes sense. Like when you increase the temperature on a body, the length will increase. So you have to add the original length upon the increased length for the final length. So when you write this formula again, it will be L alpha delta t plus the original length, as you can see, plus L. So here if you take L common, it will be 1 plus alpha delta t, and this is going to be used in case of even superficial and even volume expansion. So I won't be like repeating it for all of them. You have to basically do it by yourself. So yeah, I'll be now going for the next ones. That would be superficial, and for that the formula, as you can see, delta A is equal to A beta delta t. So here beta, you can listen to the terms carefully. Delta A would be change in area, A would be original area, and beta would be coefficient of superficial or coefficient of aerial expansion, that is beta, and delta t again change in temperature. So the same logic will be applied. A final is equal to delta A plus A. So that would be, I'm pretty sure that's obvious. When you use the same concept, it will be A bracket 1 plus alpha delta t for area final. The same thing can be applied to even volume expansion. So as you can see, it is going to be delta V is equal to V gamma delta t. Or here delta V is change in volume, V is original volume, and gamma is coefficient of volume expansion. So yeah, the ratio is given over here. Alpha is to beta is to gamma is equal to 1 is to 2 is to 3. It's given in the NCRT, so I've just written it. It's obviously going to come into help in the very next problem. As you can see over here, the application of it. Let's say there is like a ring like this, and the distance between the edges is going to be, let's say, d. So when you heat it, that's what I've denoted over here. When you heat it, what will happen is the final d, right, the distance final delta will be is equal to di bracket 1 plus alpha delta t. So this is from the same logic. Instead of L, I've used d over here. Basically d over here means the length, the distance between the 2 points. So it increases. As you can see, it's plus, so it increases. I'm just going to, like, this is not a formula, but I'm just going to highlight it anyways. So the same case, let's say there's a sphere which has in both the cases they have given some alpha, which is the coefficient of let's say coefficient of linear expansion, just like how I mentioned. So in that case, let's say there's a sphere and they've asked you what would be AF and VF, which would be final area and final volume. In this case, you don't have to worry. You can use the same formula which I mentioned above, but over here when you apply it, what will happen is instead of beta over here, as you can see, it's 2 alpha, and the reason is because, as you can see over here, beta is equal to 2. So when you make sure the ratio is given distributed, that what will happen is when you resolve the ratio, you'll be getting beta is equal to 2 alpha. So the same thing, we'll be getting gamma is equal to 3 alpha. So the same concept is used, and you'll be getting final volume as VF is equal to VI bracket 1 plus 3 alpha delta t. This, if they have given you beta directly, then you can of course write beta over here, and if they've given you gamma directly, then you can of course write gamma directly over here. It depends on whether they've given beta and beta and gamma in the question. So I'm just going to write it in the PDF because they can obviously give direct application. They would not expect you to resolve the ratio. And next one would be thermal stress. So let's say there is a rod which is in between these rigid walls, and if you heat it, what will happen is there will be a stress developed. It's called thermal stress. You can just memorize the formula because there is a derivation, but that's not required at this stage. Next one will be heat capacity, or here as you can see, heat capacity is going to be denoted by capital S, as you can see, and the formula is going to be given by capital S is equal to delta Q by delta T. And what is delta T over here? Delta T is change in temperature, and delta Q is change in heat. And the same thing if they have denoted using small s, like as you can see, this is capital S, this is small s, then it will be specific heat capacity. That's why I've written SPC dot in bracket, which means specific heat capacity. So it's the same formula, but the formula here in the denominator has m, which means just heat capacity means heat required to raise temperature by 1 degree, whereas over here it would be per unit mass. So that's why it would be equal to delta Q by m delta T. That is specific heat capacity. So same thing if it's capital C, it will be molar. As you can see over here, it is denoted by capital C is equal to delta Q by n times delta T. So here instead of m it is n, which means it is molar, and as I just mentioned, it is denoted by capital C. So that way you'll be able to use the formula. And next one, obviously there is going to be one observation made, which is going to be capital S is equal to small s times m, and that is obvious. And what is Cp and Cv? It will be done in thermodynamics in depth, but Cp means molar heat capacity at constant pressure, and Cv means molar heat capacity at constant volume. Next one will be calorimetry, and this concept you might have learned it even in 10th. It basically means heat lost by hot body is equal to heat gained by cold body. I have properly explained the short form over here. You can remember it however you want to, but this is the main principle of calorimetry. So here, let's say the hot body over here, as you can see, T1 is lesser than T2, which means this is the hot body. So I'm just going to write H over here so that you won't get confused. And this would be C. This is the cold body. So in this case, when you, let's say, pour the cold body into the hot body, and let's say the final temperature attained is just T. Listen to me carefully. Final temperature attained after mixing is going to be just T. In that case, what will happen is, and let's say M1 and M2 are the mass of both of them, it is obvious. In that case, heat lost by hot body. So as you can see, M2 small s2 bracket T2 minus T. So because T2 is hot body, you should subtract from it the final temperature. So that part, okay, you understood. And by the way, if you're wondering how this is going to be heat, it is from the above formula. As you can see, if you multiply M, if you multiply the whole thing by M into delta T, you'll be getting S M delta T is equal to delta Q. So you are just basically sending this over here. You are just sending this over here, or you can say you multiply the entire equation by M delta T, and that is equal to heat gained by cold body. So the heat gained by cold body would be M1 small s1 bracket T minus T1, which means final temperature minus the temperature of cold body. And that is because the final temperature attained will obviously be higher than the cold body, so we don't want negative sign, and that's why we write it like this. So we basically equate both of them. I'll just even highlight the equating part also, because it is important that you're equating both of them, and you can find out the value which is asked or depends on the question. You should obviously solve questions. You can watch my orientation session to know how to approach these lectures. Like once you watch them, what to do, and all of it is given in that lecture. Next one will be basic term, which would be melting, fusion. I'm pretty sure all of you know. You can just read the NCRT: boiling, melting point, sublimation, and triple point. The one which is new might be this term, as you can see over here. I'm not sure on how to pronounce it. That's why I'm just going to leave it over here. So this would be seen in application of skating on ice, and also when you pass a thread through the ice. Like I'll be just explaining right now. So skating on ice and thread would be the application, which means when you skate on ice, what will happen is, let's say this is the shoe. When the pressure is applied on the ice temporarily becomes water. So that way it will act as a lubricant, and you can move forward while skating on ice. So the same thing if you take a string, and if you slowly, if you pull the string from both the side downwards, the pressure will cause this ice to convert into water temporarily, and then after some time it will go back to the state of ice. So you can basically put a string through, or a thread through the ice without actually placing it right in the beginning. You can read the NCRT, they have shown the same example. So next one would be latent heat, and as you can see, there will be two formulae which would be latent heat of vaporization, which is given by LV is equal to Q by M, and over here latent heat of fusion, which is LF, which is equal to Q by M. Over here what you have to know is, as you can see, this graph is actually by a YouTube channel called Edunity, so I would like to thank him, and that's why I've given the credits also. However, yeah, this graph basically, there's an example. Let's say the body is at minus T1 temperature, which means it's at ice state. So ice is solid. So till A to B, right, what will happen is, let's say you start heating it slowly. In that case, what will happen is, from A to B, as you can see, observation, it's ice, so it's given as solid. At T2, what will happen is, it will start to change its state from S to L, which means solid to liquid. That's why temperature T2 is called as melting point. And next one would be CD, which means from C to D. As it's in liquid state, which would be water, I've written liquid. Same way, what will happen is, at temperature T3, it will start changing from liquid to gas. That's why it's called as boiling point. And finally, afterwards, E to F, again, it will be in vapor phase. It's obvious. I'm pretty sure you understood what this graph means. But what you have to know is how to convert the graph into equations. So just like how I mentioned, whenever phase change is happening, you have to use latent heat. Please listen to me carefully. Phase change means you have to use latent heat. So which means at Q1 over here, as you can see, the formula would be just like how we saw above. S means small s means specific heat capacity, and again there's a small s which means of the solid state. Bracket T2 minus of T1, and the same thing over here, Q3 minus Q2 would be the same thing. M small s L, which means specific heat capacity of the liquid. T3 minus T2. And however, the thing which you have to know is Q2 minus Q1, as you can see, is going to be MLF, which means the latent heat of fusion, because it is obviously melting, right? As you can see over here, Q4 minus Q3 will be equal to MLV, and that would be of latent heat of vaporization. So the formula which I just mentioned, I have just used it over here. This formula I've just used it over here. So that would be latent heat. You can use these equations to solve questions. Solving questions will give you an idea. Next, heat transfer. There is obviously conduction, and there is convection, and then there's radiation. So conduction happens when the atoms vibrate. Convection happens when one particle to another particle. And radiation, it doesn't require medium. So that's why medium required, medium not required. And over here convection is affected by gravity. That's why I've written G, and I put a check mark over there. So that would be heat transfer, and that was theoretical part. Next one would be heat current. From here it's pretty important. It was obviously important even till here, but you might have learned a lot of things in 10th grade. So heat current, you can obviously connect this analogy with current from current electricity. If you are a student in class 12, or you might have learned from Ohm's law that I is equal to V by R. From the equation you can rearrange it like this. So the same way over here, V, you can, instead of writing V as potential difference, you can write it as T as temperature difference, and R over here is going to be R thermal, which is equal to L by Ka, which means it is going to be, as you can see, this is a formula, you have to know it. It is resistance, thermal resistance, which is given by RTH, which is equal to L by Ka, and K is the constant over here. So it is dependent on the material. And as you can see over here, instead of V, it's the same thing. Heat current, we denote it by H instead of I, and instead of potential difference, we are writing temperature difference. So as you can see in the diagram, T1 is greater than T2, so T1 minus T2 divided by, instead of R, we are just replacing the formula L divided by Ka over here in the denominator. So this would be the formula for heat current, and you have to like memorize both of them, but you can use the current electricity analogy that I just gave. It'll be easier to memorize. So that would be this part. And heat flow, as you know, in current electricity, I is equal to Q by T. So the same way over here, Q is equal to H times T. This can obviously be connected with Q is equal to I times T from current electricity. Next one will be connection in series. So let's say we have connected two conductors in series, and they have area AA and L1, L2, K1, K2, and T1 and T2. In this case, R equivalent is just like how you have learned in 10th grade and everything. It would resistance, equivalent resistance, Req would be equal to R1 plus R2, and you have to just replace the formula for R which I gave you over here, thermal resistance formula. It is equal to L by K1 Ka. So the same thing would be L1 by K1A plus L2 by K2A is equal to, it's basically like R1 I've written over here, R2 I've written over here, and R equivalent I've written over here. But over here, the length, as you can see, final length would be L1 plus L2. It's not single, individual, right? So that's why in the final formula, as you can see, I've written L1 plus L2 divided by K equivalent A. And rearranging this formula, you can find K equivalent, which might be the question typically. So yeah, you can even do this, or you can directly learn the formula for K equivalent. This will be asked to find. So the same thing, you can even see connection in case of parallel conductors. Let's say they have length L, A1, A2 area, K1, K2 as their constant, and in that case, it is just like how we have learned in current electricity. The parallel connection will be given by 1 by R1 plus 1 by R2 is equal to 1 by Req, which is R resistance, equivalent resistance. So you can obviously connect it with current electricity. It will help you a lot, and it will give you an idea of how to remember it, as you have learned it in 10th grade already. So over here, I've just replaced R1, 1 by R1 formula from this formula itself. From this formula, I've replaced it over here. That would be K1 A1 by L, and 1 by R2 would be this K2 A2 by L, and 1 by R equivalent will be this formula, but obviously over here area will be A1 plus A2, because when you connect it in parallel, the area is increasing. The length will still be the same, but area is now increased, so it has increased. So that's why you have to keep that in mind. So I hope this was clear. I'm just going, and using this equation you have to find R equivalent obviously. Next one would be WDL, which means Wien's displacement law. Wien's displacement law. I'm not sure how to pronounce it, I'll be honest. So here, as you can see, the graph over here is going to be intensity versus wavelength, which would be lambda. So that would be, as you can see over here, at temperature T2 the graph is like this, and at temperature T1 the graph is like this. So when you basically try to extrapolate the maximum wavelength by using the dotted lines, as you can see over here, that's what I've done. You'll be getting the maximum wavelength over here as lambda m, which means maximum wavelength 2, and over here you'll be getting it as 1. So basically it's I've put the dots so that you'll know which one I'm referring to. So in this case, temperature T2 is greater than T1, and also you have to know that because this is observed, we can say that maximum wavelength is going to be inversely proportional to the temperature. So when you like remove the proportionality constant and multiply the entire equation by T, it will be lambda m, which is lambda m times T, which is equal to B. And B over here is basically, I'll just write it over here, B is equal to the constant, Wien's constant, or Wien's constant, and yeah, I've just written WC. So with that, we are almost done with the chapter. We can go to the next part, which would be equal to Newton's law of cooling. So in this, you have to know this equation mainly. So this equation dt by d capital T by d small t is equal to C times T minus Ts, which means over here T should be approximately, or it should be close to surrounding temperature. So it shouldn't be exactly equal to or close to, it should be somewhere around, it should be like having a small difference. So in that case, he said that rate of cooling. So as you can see, d capital T by d small t is rate of cooling is directly proportional to the difference in the temperature of the object and the surrounding, is what he said. And when you remove the proportionality constant, it will be small c. So I've written an example for the very first time. I'm giving an example because I'm pretty sure this equation just as it is won't explain much. So let's say there is an object which is, let's say, cooling from 75 degrees Celsius to 65 degrees Celsius in 5 minutes at temperature 25 degrees Celsius, which is room temperature. So if they've asked you what is temperature after 5 minutes, you have to write two equations. I'm just going to highlight the equation, which ones you have to know. First equation that you have to write is to solve and find small c, which is the and then the next one would be to solve for capital T. That would be step number 2. So for step number 1, what you have to do is you have to just use this formula. As you can see, d capital T, which means 75 minus 65 divided by d small t. Over here it's given 5 minutes, so I'm just going to underline the values. I've just substituted it over here. So 75 minus 65 by 5 is equal to small c bracket. Over here T would be average temperature. Like they usually would have given you two temperatures, so that's why I've just written average temperature. And yeah, that is like the summary of it. So average temperature, as you can see, would be 75 plus 65 by 2 minus 25 degree, which is surrounding temperature, and I've written it over here in the question. It will be given as room temperature, so that's why it's 25. So that was that was pretty obvious, 25 degrees Celsius. So you'll be able to find C, and the value of C came out as 2 by 45. So for the second equation, you have to find the temperature after 5 minutes. So you have to write the same equation, but this time the body is already at 65 degrees Celsius. So 65 minus T divided by 5, because they've asked you after 5 minutes. So divided by 5 is equal to value of C, which you found out from equation 1, times the average. As you can see, its average is found out in the same method like how it's done above. 65 plus T divided by 2 minus 25, which is the room temperature. So this time you have to solve for T, and you'll be able to get the value of capital T, which is the temperature after 5 minutes. You can solve questions to understand more. Next one would be SBL, which means Stephen Boltzmann law. Over here, as you can see, there is a body and it has it gains temperature Ts, and it even radiates temperature, which is given by this equation. Net rate of heat loss, this is called as rate of heat loss, d capital Q by d small t. So that would be equal to rate of heat loss, and Ts, which would be the one, as you can see the arrow is denoting the direction, it is equal to this, which is going to be the Stephen Boltzmann constant times basically this would be the equation, which would be sigma times E times A times Ts to the power 4. And the same thing, actually my undo button is not working, like when I press it's not working, so that's why I'm resorting to just erasing it and doing it again. And as you can see, dq by dt, once again I've written, is equal to sigma times E A T to the power 4. So these two aren't the formula which you have to remember. Instead you can just go for the formula which is given over here in the bottom, which would be net rate of heat loss. So basically this is going to be equal to this formula. Net rate of heat loss is equal to this formula, and this formula is going to be the formula which you have to know. Dq by dt is equal to sigma times E times A bracket T to the power 4 minus Ts to the power 4, and the reason is because T is going to be less than capital Ts. So one more thing is, there is something called as Mayer's equation, which I'll be doing in thermodynamics. So all of that heat capacity and everything will be gone in depth in that chapter. So I hope you're able to understand this chapter. Please share it with your friends, like it, subscribe. I've put in a lot of effort, and it will benefit the community as a whole. So keep working hard, and I'll see you in the next lecture. So yeah, see you.